in. Dear friends, in previous class we already discussed the different arithmetic function or number theoretic function, arithmetic function or number theoretic function, Mobius function and Euler-Torsion function. So, what is an Euler-Torsion function? Euler-Torsion function means it is usually denoted by phi of n, and it is the phi of 1 is defined as phi of 1 equals 1, and phi of n is defined as the number of positive integers less than or equals n and relatively primes to n. Means the number of positive integers not exceeding n. It is less than or equals n, not exceeding n and relatively prime to n. This represents as sigma phi of n equals sigma k ranges from 1 to n. Sigma k ranges from 1 to n of 1. So there is a symbol. This symbol denotes the sum is extended over those k which are relatively prime to n. So in previous class we discussed the different values of 5 values of n, means phi 1, phi 2, phi 3, phi 4, etc. and so on. Now there is a result. If n greater than or equals 1, if n greater than or equals 1, we have sigma d divides in phi of b. Sigma d divides in phi of b equals n. This is the requirement. Sigma d divides n, phi of b equals n. So for this proof, we define a set S. Let S equals set 1, 2, 3, etc. up to n. Then divide this set S into disjoint sets as follows. That is, some A of D equals set of all k such that k GCD of k and n equals D, where 1 less than or equals k less than or equals n. Set of all k such that GCD of k and n equals D with 1 less than or equals k less than or equals n. S is a set which consists of the first n natural numbers, and we can divide this S into number of disjoint sets like this. A of D equals set of all k such that GCD of k and n is D, where k ranges from 1 to n. So consider this one, set S equals set 1, 2, 3, etc. up to 10. If you consider set S is this one, and what is A of 1? A of 1 means set of all elements in this S which have a greatest common divisor 1 with the last element or the highest element 10. So A of 1 and 10, GCD of 1 and 10 is 1. GCD of 3 and 10 is 1. GCD of 5 and 10 is 1. GCD of 7 and 10 is 1. GCD of, not 5. GCD of 7 and 10 is 1. GCD of 1 and 10 is 1. 3 and 10 is 1. Then GCD of 7 and 10 is 1. Also 9 and 10 is 1. So A of 1. Set 1, 3, 7, 9. What is A of 2? A of 2 equals the A of 2, here GCD 2. Which elements in this S has GCD 2 with a 10? 2 and 10 has GCD 2. 4 and 10 has GCD 2. 6 and 10 has GCD 2. 8 and 10 has GCD 2. So there are again 4 elements. What is A of 3? A of 3 is an empty set. Why? Because there is no element in S has GCD 3 with the highest element 10. So A of 3 is an empty set. A of 4. A of 4 is again an empty set. because there is no element in S has GCD form with the element 10. A of 5. What is A of 5? A of 5 equals singleton set 5. The element 5, only the element 5 has GCD 5 with a 10. 6, 7, 8, 9. No such elements, no such GCDs are exist, and A of 10 equals singleton set 10. Okay. So here, this S divided into these 4 mutually disjoint sets. A1 union, A2 union, A5 union, A10 equals S, as well as their intersections. A1 intersection, A2 is empty, and they are pairwise disjoint. So all of these sets are mutually disjoint, and their union is nothing but S. So S can be divided into number of these sets. So generally, if you consider S equals set 1, 2, 3, etc. to n, then you can divide that S into disjoint sets like as this A of D equals set of K, with the K and N is GCD of K and N is D, where K ranges from 1 to n. That means this A of D contains those elements of S which has GCD with the n. Then the set A of D forms a disjoint sets. Okay, so S equals, moreover, S equals union A of D. Union of A of D. Further, this A of D's are mutually disjoint. Now let F of D denotes the number of elements, the number of integers in A of D. Let F of D denotes number of integers. Number of integers in A of D. Number of integers in A of D. So how many integers in A of D? How many integers in A of D? In A of 1, there are 4 elements. Okay. In A of 2, it is 4 elements. In A of 5, only 1 element. In A of 10, there is again only 1 element. So how many elements in totally in this A of 1, A of 2, A of 5 and A of 10? There are 10 elements. This 10 elements means that elements are same as in set, the given set S. So we can say that sigma D divides n, F of D equals n. Okay, let F D denotes the number of integers in A of D. Then from this example, it is clear that sigma D divides n, F of D equals n. Okay, but what is GCD of K and n? It is given GCD of K and n equals D. That means GCD of K by D, n by D is 1. K by D and n by D are relatively primes. Put on Q equals K by D. Q equals K by D. So 0 less than or equals K less than or equals n implies 0 less than or equals K by D means Q less than or equals n by D. Why? Because of this choice. Q equals K by D. So 0 less than equals K less than equals n implies 0 less than or equals K less than or equals n by D. So since Q equals K by D, then there exists, since Q equals K by D, there exists a 1-1 correspondence between the elements in A of D and those integers satisfies 0 less than or equals Q less than or equals n by D. So listen, in A by D, the number of elements in A by D and the elements which satisfies this condition has a 1-1 correspondence. Why? So like this, A of 1 is 1, 3, 7, 5. When D is 1, when D is 1, here 0 less than or equals 0 less than or equals K by D less than or equals 0 less than or equals K by D less than or equals n by D. 0 less than or equals K by D less than or equals n by D. So when D is 1, from this example, what you get? 0 less than or equals K less than or equals n when D equals n. So this A of 1 consists of how many elements? 1. There are 4 elements. They are 1, 3, 7 and 9. And the elements in this A of 1 has a 1-1 correspondence with this 0 less than or equals k less than or equals n. Means 0 less than or equals q less than or equals n by d. So the elements in are 1, 3, 7 and 9. Which satisfies the elements in S which satisfies this condition is also 1, 3, 7 and 9. So there is a 1-to-1 correspondence. So immediately we can conclude that there exists a 1-to-1 correspondence, 1-1 correspondence between the elements of A of D and the integers which satisfies the condition 0 less than or equals q less than or equals n by d. So number of such q's, this number of such q's is phi of n by d. Euler-Torsion function. Okay, phi of n by d. Therefore, number of such elements is nothing but that is f of d. Therefore, f of d equals phi of n by d. Number of such elements is f of d. So f of d equals phi of n by d. Therefore, sigma d divides n f of d equals sigma d divides n phi of n by d. But actually, what is sigma d divides n f of d? That is n. So means sigma d divides n phi of n by d equals n. But we have to show sigma d divides n phi of d equals n. But here we obtain sigma d divides n phi of n by d equals n. But what is d? D is the GCD. So this d runs through all divisors of n. Here since d be the GCD of k and n, so d runs through all divisors of n means d runs through all divisors of n by d. Okay, since d be the GCD of k and d runs through all divisors of n, that means d runs through all divisors of n by d itself. So phi of n by d is equivalent to phi of d. Phi of n by d is equivalent to phi of d. So you can replace this phi of n by d with the phi of d. So we have this result, sigma d divides n, phi of d equals n. That is the proof. Okay. Yes. Now there is this is the first theorem relating Euler-Torsion function. Now consider the another one. The relation connecting phi and mu. How to connect this phi and mu? Relation connecting phi and mu. So there is a result. If n greater than or equals 1, then phi of n equals sigma d divides n phi of mu of d into n by d. Sigma d divides n mu of d into n by d. So this is the result. If n greater than or equals 1, then phi of n equals sigma d divides n mu of d into n by d. So how? So for this, the proof is in this way. What is phi of n? By definition, the Euler-Torsion function phi of n equals sigma k ranges from 1 to n of 1. This indicates k runs through the elements into that are relatively prime string. Okay. Then sigma k ranges from 1 to n 1. This can be rewrite as sigma k ranges from 1 to n greatest integer of 1 by GCD of n. Okay. Why? So what is here? Sigma k ranges from 1 to n of 1 according to this symbol. That symbol means it indicates the sum is extended over those k which are relatively primes to n. So here this can be rewritten as sigma k ranges from 1 to n, greatest integer 1 by GCD of nk. So for if GCD of n and k equals 1, they are relatively prime, then what is this greatest integer of 1 by GCD of nk equals greatest integer 1 by 1 equals 1. Okay. If GCD of n and k differs from 1, that is greater than 1. Then greater than differs from 1 means it is greater than 1. So what about this greatest integer of GCD of 1 by GCD of n and k? That is GCD of 1, a number greater than 1, that is always So you can define this phi of n equals sigma k ranges from 1 to n of 1, that is sigma k ranges from 1 to n, greatest integer 1 by GCD of n. This definition is this is due to this property. Okay. Therefore, we have, but previously we proved sigma d divides n mu of d. What is sigma d divides n mu of d? Sigma d divides n mu of d is greatest integer 1 by n. Okay. Therefore, sigma d divides GCD of n and k of mu of d equals greatest integer 1 by GCD of n and k by this definition. So come to this one. Therefore, what is phi of n? Therefore, phi of n equals sigma k ranges from 1 to n, and phi of n, sigma k ranges from 1 to n, then sigma, okay, what about a sigma k ranges from 1 to n of 1 by this one? That is sigma k ranges from 1 to n, sigma d divides GCD of n and k of greatest integer 1 by GCD of n. Okay. Or more generally, can we again rewrite as sigma d divides n mu of d equals greatest integer 1 by n. Therefore, sigma d divides n GCD of n and k mu of d equals greatest integer 1 by GCD of n and k. So again we can rewrite as this phi of n. How? So phi of n equals sigma k ranges from 1 to n, sigma d divides GCD of n and k of mu of d. Okay, supply. Therefore, phi of n equals this one. That means this phi of n can be again rearranged as phi of n equals sigma k ranges from 1 to n, and sigma d divides GCD of n and means sigma d divides n and sigma d divides k of mu of d. Okay. D divides GCD of n and k means d divides n and d divides k. So for a fixed d, the divisor d of n, we must sum over all those k in the range, k ranges from 1 to n, so which are multiples of, k ranges from 1 to n, which are multiples of d. So if you write k equals qd, k ranges from 1 to n, and k is a multiple of d, k equals qd, then k ranges from 1 to n implies 1 less than or equals 1 less than or equals q less than or equals n by d. Okay, where k equals qd, q by d equals k, so 1 less than or equals q less than or equals n by d. Hence, this sum phi of n equals sigma k ranges from 1 to n, sigma d divides n, and d divides k, mu of d become, that can be written as phi of n equals sigma, then this can be rewrite as, this sum can be rewrite as sigma, d divides n, sigma d divides n, and sigma q ranges from 1 to n by d of mu of d. Q ranges from 1 to n by d. So this sum can be written as phi of n equals sigma k ranges from 1 to n means sigma d divides n, and sigma q ranges from 1 to n by d. So sigma q ranges from 1 to n by d of mu of d. So that is same as sigma d divides n. This rearranged as sigma d divides n mu of d into sigma q ranges from 1 to n by d of 1. That equals sigma d divides n mu of d into, what is this one? It is n by d. Thus, phi of n equals sigma d divides n mu of d into n by d. So this is what we reduce. So this is the proof. Okay. So these two theorems are so important. So this, if n greater than or equals 1, phi of n equals sigma d divides n mu of d into n by d. GCD of n by k by using this property. So sigma d divides n mu of d equals 1 by n. So sigma d divides n GCD of n and k is of mu of d is greatest integer 1 by GCD of n and k. Therefore, this definition phi of n equals sigma k ranges from 1 to n. GCD of greatest integer GCD of 1 by n k is nothing but sigma d divides GCD of n and k of mu of d. Okay. So by using these arguments, finally we have phi of n equals sigma d divides n mu of d into n by d. Okay.